Hello everyone, my name is Osama Shahid and I will be presenting our paper OpenLoRa, validating LoRa implementations through an extensible and open source framework. It's a joint work with my lab mates Manan Mishra, Daniel J. Koch, in collaboration with Krishna Chintalapudi, Professor Suman Banerjee, and my advisor Bhuvana Krishnaswamy. Recently, a number of applications have called for long-range and low-power communication. For example, smart agriculture. Smart agriculture requires connectivity of soil health sensors spread over several square kilometers. Similarly, in order to build smart homes and smart cities, we need to connect IoT devices spread over large distances. To address the needs of these applications, recently, a number of communication protocols have emerged, amongst which LoRa is the dominant one. LoRa is quite popular since it is able to operate at large distances of tens of kilometers, and it supports long battery life as well. Therefore, it checks all the boxes that are required for the application scenarios we are focusing today. Typically, LoRa networks are deployed at large scale. Consider this field scenario in which multiple soil health sensors are deployed in a vast field. All of these sensors will be sending their data to the nearest base station. In LoRa networks use basically Aloha-based MAC protocol, in which transmitters transmit whenever they have some data to send. Such sort of MAC protocol works well when there are few nodes in the network. Recently, some of research works have highlighted the challenges that are faced by LoRa networks. For example, Ghina et al. Mentions that as the number of nodes in a network increase, packet reception rate decreases exponentially. Packet reception rate is proportional to the network throughput. Therefore, network throughput decreases exponentially as well. Similarly, another work mentions that as the number of nodes in a network increase from 200 to 2,000 devices, throughput decreases. And increasing the number of gateways does not improve the throughput significantly. The reason for this drop in throughput is basically packet collisions. As I just mentioned, that LoRa uses Aloha-based MAC protocol. In such sort of MAC protocol, end devices lack coordination. Therefore, as the number of devices in a network increase, the probability of multiple nodes trying to talk at the same time increases, and therefore leads to packet interference. To address this scalability issue, recently a number of LoRa demodulator implementations have emerged. We broadly categorize them into two categories. Under the first one, a few of the instances are CIC, co-LoRa, N-Scale, and FRAC. They try to improve network throughput by resolving LoRa packet collisions. Under the second category, some of the instances are CHARM, NE-LoRa, Ostinato, that increase network throughput by improving LoRa range of weak LoRa links. Previously, I have worked on a research project that increased the throughput LoRa network throughput by resolving LoRa packet collisions. The first work, CIC, is an outcome of that research project that I've worked on. I would like to spend some time to discuss how LoRa's transmitter and receiver pipeline looks like. At the transmitter end, the bits of the message to be sent are encoded in a specific format, then converted to symbols. Those symbols are then fed to LoRa modulation block. This modulation block modulates the symbols using chirp spread spectrum modulation and converts the symbols to raw IQ samples, which are then transmitted over the air through an antenna as electromagnetic signals. These signals are then captured by a receiving antenna, and the raw IQ samples are fed to LoRa demodulator block. And the reverse process is performed until eventually we get decoded bits at the output. It must be noted that the new LoRa implementations that I have discussed in the previous slide, they try to replace this LoRa demodulation block, or they try to suggest changes in this LoRa demodulation block. And for the specific cases of LoRa demodulators that improve the network throughput by resolving LoRa packet collisions, they replace the decoders by a parallel stream of multiple decoders. So although we have multiple LoRa demodulator implementations at hand, it is still quite challenging to compare all of them and assert which demodulator performs better than the other. For example, if we discuss the implementation platform, some of the works are implemented in MATLAB or C++, others in Python or GNU Radio. Also, the evaluation scenarios for each one of them is different. Some evaluate their algorithms in an outdoor scenarios, others in indoor scenarios, and the dimensions for each of these scenarios is different as well. And finally, they report their results in terms of different metrics. They don't speak the same language when we discuss their results. So it can be noted that there exists a lack of unifying platform where we can compare all these existing works. This motivated us to develop OpenLoRa framework, where so far in OpenLoRa, we have integrated 4 collision-resolving LoRa demodulators that are CIC, CoLoRa, FTRAC, and N-Scale. In OpenLoRa, regardless of the implementation platform in which these works were originally presented on, we provide a unifying Python implementation for all of them. And also, we have added a flexibility to each of these algorithms to accept any data set that contains LoRa packet collisions. And also, at the end, we provide users with the choice of choosing a metric out of a list of metrics through which they can report their results. So the implementation of our framework can be found at the link as openlora.wisc.edu. Our framework consists of 4 main blocks. The first block is config.py. Config.py block configures the LoRa signal parameters and also chooses the data set with which the users want to work with. The next block is master.py. Master.py is the engine of OpenLoRa. This block accepts raw IQ samples from a .dat file format and feeds it to packet detection block. Packet detection detects packet and feeds each packet to the demod.py block. Demod.py runs multiple algorithms of LoRa demodulation and feeds this, and at the output, it feeds the symbols to the decode.py block, which decodes the input symbols and feeds the bits to the metric.py block. Metric.py block eventually computes the results in terms of different metrics that the users choose. In OpenLoRa, we have collected data sets from a diverse set of scenarios and collected such data set with varying level of SNRs and varying level of packet collisions. We have made all this data set publicly available. We hope that in future, researchers can use our data set to test their new LoRa demodulation implementations, or may use our data set to compare existing LoRa demodulation techniques as well. For each of these scenarios, we use commercial off-the-shelf LoRa boards as transmitters and software-defined radios as the base stations. Now, I would like to, in order to give a better understanding of our framework, I would like to give a demo video. Users can access our implementation at the site, as I mentioned earlier, openlora.wisc.edu. If we go to that site, we can go to Software Repository tab. Under this, we present links to our Docker Hub implementation, GitHub repo, and datasets. Let's explore datasets. It's a Google Drive link in which, if we go to the datasets folder, here users can find all the datasets that we have captured. And for each of these datasets, we are providing a README file as well. For the purpose of this demo video, I will be choosing a dataset of indoor scenario and will be downloading it into my system. Once the dataset has been downloaded, now we can go to the Docker Hub, copy this command, and this command can be used to pull the Docker container of OpenLoRa. We'll paste it, and it will pull the Docker implementation of our framework. Once it has been pulled, I'm using Docker Desktop app to figure out this implementation. So as you can see in the Docker Desktop app, our implementation is already there. Under the file section, we start off by first importing the data set that we have just downloaded. So I will be importing the data set that I have for the indoor scenario that I just downloaded. Once it is there, the second data set is the one that I'll be using for this demo video. We will then first go to the first block of OpenLoRa, which is config.py block. Within this, the first 5 parameters specify the parameters for the LoRa signal, and the values for these parameters can be found in the README file. The input file variable specifies the data path to the data set that we want to work with. And now I will be setting the data path to the data set that I've just imported into my container. Once I've set the data path, the last variable, that is output file, specifies the name of the file to which we will be writing our matrix to. Once config.py file is set up, the next block that comes up is master.py. Master.py is, again, as I mentioned, is the engine of OpenLoRa. Within this block, we are calling multiple LoRa demodulators. For example, the highlighted section is calling standard LoRa, and similarly, the second highlighted section is calling CIC. Similarly, within this file, we are calling all the demodulators that are like co-LoRa, F-track, and N-scale. For the purpose of this demo video, I will be commenting out the rest of the demodulator algorithms and will be only running standard LoRa and CIC. Once we have selected our demodulators, we are good to go, and we can run this container. Once we run it, it will first run standard LoRa on the dataset that we have selected. And after waiting for some time, we will be getting results for the standard LoRa. And the highlighted part shows the results for standard LoRa. If we wait for some more time, we'll be able to get the results for CIC as well. And again, the highlighted part shows the results for running CIC on the dataset that we have just selected. Now, if we go back to the file section, we should be able to get the output file that we specified in the config.py. If we open it, on the columns of this Excel file, we can find the results of each of the metrics. And the different rows show the results for different demodulators that we had selected in the master.py block. I hope this gives an idea of how to use our framework. Now, so far, we have discussed how users can use existing LoRa demodulator algorithms to run in our framework. Users can come up with their own new demodulator implementations as well and can integrate those into our framework. The bottom of this slide shows how to call the new implementations. Specifically, each demodulator takes in 5 input arguments. The first one is raw data, which are the raw IQ samples. And the rest of the parameters are sampling rate, bandwidth, spreading factor, and payload number that are LoRa specific. At the output, we have a symbols variable, which stores the symbols for each of the demodulated packet given out by each of the demodulator. We also wanted to check the correctness of our framework as well. So in order to do that, in our paper, we present this cross-validation section in which we pick key scenarios from each of the work and try to recreate that. In the slide, the orange plots show the results, the key results presented in each of the respective paper, and the blue plots show the results recreated by OpenLoRa. It can be observed that the results recreated by OpenLoRa match very well with the results presented in the respective paper. Therefore, this practice validates the accuracy and correctness of our algorithm. After establishing the accuracy and correctness, we went on to apply all the data set that we had collected onto each of the demodulator, and then collected results for each of the metric. This practice actually highlighted some of the key insights that were not presented in each of the works. For example, in this slide, the results that I'm showing reflect that for extremely low SNR scenarios, all the new LoRa demodulator implementations fail. They don't perform as well as mentioned in each of the works. And standard LoRa, the naive form of LoRa demodulator, outperforms all of them. Similar insights are also, some other insights are also discussed in the paper, and the reasons for them as well, we discussed that in detail in our paper. We also believe that there are some limitations to our framework. For example, we don't have an exhaustive list of metrics to evaluate. For example, we think that there is still some room to add other evaluation metrics like computational time complexity, which is a key metric if we want to assert that which demodulator can be deployed outdoors in real scenarios. With that, I would conclude my presentation. Thank you all for your time, and I'm happy to have questions if there are any. Thank you.